Back to the seminar. So we will have a look at how to define variables, create a code, and how to create a model to obtain solution and review results. Of course, we are interested in this same task one, which is to calculate elastic properties. And we will calculate longitudinal and, if we have some time, also the transverse modulus. But you should get the idea just from one example how it works. So what we will be looking at will be this two-dimensional model to calculate the longitudinal modulus of the UD composite. So this model will consist of two phases. As you may know, we have the fiber phase and the matrix phase, and we are going to apply loading in the fiber direction so that we get the longitudinal response. And once we have created the model, applied the loads, we will be able to calculate the elastic modulus and the Poisson's ratio just by doing some operations with our results. So this is the geometry of the model. As you can see, we have these two rectangular objects in a way. And here we have some kind of key points, 1, 2, 3, 4, 5, 6. And these key points fully define the geometry of this. But just by joining the lines through those key points, we are able to represent this geometry for this calculation, for this model. And then later we will also look at the second model. But now let's focus on this model, which is for calculation of the longitudinal modulus. I can show you right away a code. Let me see. I will drag it in the window which I'm sharing. This is how a code looks like for the ANSYS APDL. So in lengthwise, I mean, it's the same amount of work as in the MatLab to do the same calculation. But the difference is it's a, let's say, completely different programming language. I think it is somehow related to the Fortran language that ANSYS is using, but it's not exactly the same. How do we, I mean, what is the connection between this text file and the ANSYS interface that I showed you before? Well, the connection is the following. I can show you. You can still use this interface. On the left-hand side, you have the main menu. You have the preprocessor where you can choose, for example, modeling, create, well, if you want key points, or you can create areas, rectangle by 2 corners. So, well, I just created a 2D model with one rectangle. I can, I don't know, add a second one, and I can say that this, but this is, you know, I was just operating here with the mouse, and I was not able to really I was able to control the size of it, but not that accurately as I would like. And also, what would happen if I suddenly need to change the size of it? If I want to change the volume fraction and one phase is bigger than the other, what would I do then? Then I just need to clear everything and start from the beginning. And you can do that, like File, Clear, and Start New. And then you'll have such window. You can just select Do Not Read File and OK. And then say yes, we execute. So we just clear and we have a new window, and then we start another calculation with different parameters. But it's not that efficient. Instead, we will be working with these text files where we define all the parameters here, and when we need to change anything, we just change the value of the parameter, and we can then read in this file in the ANSYS software APDL, and we will get the result without doing everything from the beginning. We just change the value of the parameter, we save it, and we run it in. So this is the way we are going to learn ANSYS, actually, by writing these codes and then reading them in through the following way. You can go to File, Read Input From, and then you specify the file. Well, in my case, it is going to be quite a long trip. I can just find our course and the year. And for example, this text file, which I showed you, I specify it, I say OK. And what you see, well, everything is calculated. Of course, it's calculated because I already created the file. And we now need to have a look in this file, what is going on really there. And you see the nice rainbow colors, of course, because we applied the loading in longitudinal direction. And but we'll get into the details. I'll clear it, and we start from the beginning by looking at this input file. So of course we start from the top, and the first command you will see, and this is just basically a notepad. You can use any other text editor which you are using, it doesn't matter. That's also actually, in a way, it's an advantage that you can really write this code in a text editor if you know the language. You don't need to buy the software, you just know the language, you write the code, and then you can just send it to someone who has it, and you can get the result. But that's not the main point here. So let's focus on the code. The first line there is finish, and that is an ANSYS command, and that means that we finish whatever processor we were into, like preprocessor, solution, or the post processor, the three main blocks. It kind of resets it back to the beginning stage. And the second one is you can see this / and clear. That will clear again the workspace in a similar way as MATLAB clears the workspace using the CLC command. Okay, just by these first two commands, they will not do much. They'll just clear the workspace in a way. And then we have the third command there, which is this preprocessor. It's called prep7. Well, it's for preprocessor, and 7. Well, it's just historically the number of this processor is. But I mean, you need to issue this command in order to arrive to the preprocessor. And preprocessor is a stage when we define the geometry element type, we create the mesh, we apply the boundary conditions, and once we're done with them, then we move on to the next stage, which is the solution stage, where we actually do the solution. So remember, the preprocessor in any commercial software is the first stage, and in ANSYS APDL language, this is how you enter the preprocessor stage, by issuing this command, this / preprocessor 7. Of course, it may be a little bit intimidating to see, okay, you get completely new language, and it's not really intuitive what this what you need to write. So I will just, for the sake of demonstration, open the ANSYS help. So it will take a while to load. I will drag it in. It was loaded in another screen. So you see this ANSYS help, quite a big resource for you. But again, each module has its own help, and it's all accessible here. Instead, you need to find where you have this mechanical APDL. This is where you have all the help topics for the mechanical APDL, and then you have the topics, and each has this subtopic and so on. So what I can suggest to you, if you are willing to find a command which is doing some certain operation, you can refer to the command reference and find this command here through just by browsing through. Of course, it's a lot of commands, and we'll not have a look at all of them. But let's say we go to the commands starting with the letter P, and we can find this, the command that we already had a look at. It's this. This is the command, right? The preprocessor 7. And you see in the help, this is the command, and there is an explanation that this command enters the model creation preprocessor. Okay, so in the same way, whatever command you, for example, see, you can always find the description, what this command is doing and how to write it correctly here in the ANSYS help. I will minimize it for a moment, but we'll come back to help quite frequently. Now back to the input file. This is then the first thing we created. We entered the preprocessor. And then I have a new stage here. I'll have some exclamation marks. That doesn't mean that I'm that it needs a lot of attention or that I'm screaming. It means that it's just the exclamation mark is actually a symbol that separates command from comment in ANSYS. So in the MATLAB it was %sign. In ANSYS APDL it is the exclamation mark. You don't need to write 3 exclamation marks, and you don't need to write them here, but it's just my the way I have done it here. What matters is that you have the exclamation mark at the beginning of this line. So ANSYS will ignore it, but it will be in the file. So you can structure your files in a way that you understand them yourself later on, and that you can also send them to another person, and another person is also able to figure out what is being done. It's the same as in MATLAB. You just need to write comments in order to kind of explain what you're doing, because of course you are not, if you're not using this language every day, you will not be able to memorize. So it's just, you're just benefiting from writing these comments. And then below, well, given means that these will be the input data. And below, you see here, I'm writing as this. So we have this VF equals 0.55. And then at the end of this line, I had exclamation mark. That's the fiber volume fraction. Okay, so this is the way I define a new variable called VF, which will be the volume fraction. And the same way, Rm equals to 1, that's a matrix radius. You don't necessarily need to work with capital letters. It's just a matter of convenience and your preference, actually. So in the given numbers, I have also this Rm equal to 1 as a matrix radius. It's 1 unit, as we also had in the MATLAB calculation. The outer radius of this 2-cylinder assembly is equal to 1. And then Rf is Rm times the square root of Vf. So it's more or less identical to MATLAB. So the simple adding, multiplying, subtraction, dividing, taking a square root or power function, they are the same as in MATLAB. So this is how I define the radius of the fiber. Well, why is it this square root? You know already from the previous example that this is, if we assume the outer radius equal to 1, then we can calculate the fiber radius using this equation, which involves the volume fraction. And then I also have one more parameter, which is the L equals to 0.2. That is the length of the model. While in the MATLAB code, as you may have noticed, we never had any parameter specifying the length of the model. That's because we don't have this length dependency in the CCA model, and this is not really a parameter. However, in finite element calculation, the geometry needs to be finite. We cannot really work with infinite length. So for that reason, we will just put a certain length, in this case 0.2. It doesn't really matter. I mean, it's a small number, just not to use too much space, because you remember you have a student version, so you're a little bit limited in terms of the number of elements. So it's better to create as, let's say, small models as possible, so that you can later on refine the mesh better, instead of creating unnecessary, let's say, volume, which is not contributing to the accuracy. Okay, then we can just go to the, we are still in the input phase where we are creating new parameters in this APDL language. Here you see an, let's say, an interesting approach, or an interesting way you can define the pi constant, well, 3.1428 and so on. If you want to do it really accurately, you can write this type of function. So it's an arc cosinus of -1. Well, that's a mathematical definition of the pi constant. And you see, just by defining it as this, you don't need to specify all the numbers, but it will be the most accurate representation of the pi constant possible. So why not to be as accurate as possible? So, but alternatively, you can just define that the pi constant is equal to 3.1428 and so on. And then below we have the fiber elastic modulus, fiber transverse modulus, and so on. So basically all the fiber and the matrix properties are defined here. And then also we have there the epsilon L, which is 0.01. So I select 1% of strain. That is the applied longitudinal strain. And then the corresponding displacement, which comes from this strain, is when you multiply the strain with the length, you will get the applied longitudinal displacement. Because in any finite element calculation, it's difficult to apply strain. It's much easier to apply the displacement, which leads to a certain strain. So this is the way how to do it. You define what strain you want to apply, but then you recalculate what will be the displacement that you need to apply in order to obtain this strain. So, okay, and the last parameter there is called the parameter which I named arbitrarily f is equal to 100, and that is what I call the mesh refinement factor. We will get to that pretty soon, actually. And well, I can tell right away that if you remember the lecture that we had a small talk about the okay, yeah, I'll just finish my thought, and then I noticed that we have a question. We had a small talk regarding convergence analysis, right? That when you create a finite element model, you don't know exactly how much more you should refine the mesh. Is it going to be accurate or result already, or is it maybe inaccurate? So for that, you need to parametrically somehow control the size of the mesh, and we will do that by help of this mesh refinement factor, as you will see later on. Now I'll focus on your questions. So yes, I see that. Yeah, there's a comment that well, some of you have worked with Workbench. Well, I mentioned that Workbench is a nice and convenient tool to do, especially like it's much more convenient to do like if you have 3D objects, or if you need the CAD integration. It's much better, and it kind of, I mean, sometimes it's easier to apply boundary conditions with the workbench interface, because to apply it in APDL, it requires quite a lot of knowledge for some more complex problems. On the other hand, how workbench is working. Workbench is, okay, you create the geometry, you apply the boundary conditions, and then the workbench kind of assembles all this information, and as you press solve in solve the problem button in workbench, what it does, it converts the problem to the APDL language. So it is sent to APDL where the solution is done, and all the results are then again collected and exported back to workbench. So as a solution engine, it's still using the ANSYS APDL. And you can also integrate some of the commands. There's a special kind of section in workbench where you can input the APDL commands, kind of have a better parametric control of your workbench model. But I would say the APDL is the headquarter where all the calculations are being done. There are more convenient models, but modules and ANSYS, but still all the calculations are mainly done in APDL. This is where that's the engine of the ANSYS, you can say. Then I have a next question there. Is it more convenient to work with Pascal instead of GPA? Yes, that's a reasonable question here. It depends. I'm here using Pascals, as you may have noticed. So 300 E9. You can, of course, work with other units, but here we also have the length and the stiffness, so you have to always be consistent what system length system you are using and unit system, so that later on when you are getting, for example, stresses, you need to understand exactly what will be your units. So by default, my preference is to work with the SI units. So you work with meters, pascals, and so on, so that you have no doubt about, or I mean, you don't need to do a recalculation or adjustment. But the downside of using pascals, especially in composites, is that the stiffness values are usually quite large. So when forming stiffness matrices, where the inverse and compliance matrices, where you have the inverse of the stiffness parameters, you may get the problem of mathematical accuracy, that the numbers will be so small and that there is some kind of accuracy. I mean, if the number is too small, you may get inaccurate results. So, but ANSYS is usually good in terms of issuing a warning if there is some problem with the units that you have using too large numbers or too small numbers. You will get the warning that ANSYS is having problem with that. So in this example, we will be using just pascals so that we don't need to worry about our results in what units we are. We know that it will be in SI units. Okay, so far we did look at the inputs, so just given numbers and some, and also we had a look at some simple mathematical expressions, how they are entered in this APDL language. You can, for example, also copy paste whatever you want in the command window here in the interface. For example, I go here, I can just Control-C, Control-V and enter, and it will read in the data, but well, nothing happened because we have not yet created any geometry. We just defined some parameters. So where are these parameters? There are two ways to see them. One is just to use this graphical interface go to parameters, and let's say scalar parameters. Then the window pops up where you see the values of the parameters that you have defined, and these are the parameters I specified in the file. Or you can also write the status command, which will also bring up another window where you can see the values of the parameters. But right now it's not so important because we have not created any geometry yet. And we will do that right now. So the next stage here, after we have defined the inputs, are the key points. We start creating geometry from the bottom up. So we start from the key points, then from those key points we will create lines. From the lines we will create areas, and then we will mesh those areas. So the key points are defined using the command in ANSYS, which is called K command, so very simple command. And to find more about it, you just refer to the help. We can go and check where the K command is here in the, here it is. So we can read that K command defines a key point. So you have the command, and then we need to specify some more stuff here. It says number of the point, and the X, Y, Z are the key point location in active coordinate system. So we have Cartesian coordinate system active by default, and NPT is just the number of the point. So going back to the this key point creation stage here, we see that we create key point 1 located at X, Y, Z coordinates equal to 0. And then we have key point 2 equal to R, X coordinate is RF. The Y coordinate is 0 and the Z coordinate is 0. Well, all the Z coordinates will be 0 because we have a 2D model. So we only have X and Y coordinates, which are non-zero sometimes. And this is related, of course, to the geometry here. We are assuming that this is when we have the key point 1. Underneath here, we have the origin of the coordinate system. This is where the X and Y is equal to 0. And then the value of the X coordinate for the second key point is equal to RF, and for the third key point equal to RM. And then for the key points 4, 5, 6 is the same X coordinates as for 1, 2, 3 respectively, with the difference that we also have the Y coordinate, which is equal to the L. So this is how it is written here. So I can also write copy paste this now in the ANSYS here in the command window, and you see here, probably you see, I hope you see, it's 1, 2, 3, 4, 5, 6. So you can see the key points as they have been defined. So once we have the key points, we can go to the next stage, which is to define the lines. For defining lines, you have, well, there are different options. I'm here using in this example the straight line command, which is LSTR. And if you go back to the help to read more about this command, we can browse and search where it is. Here it is. So you see that this LSTR command uses two input fields, this point 1 and point 2, and it defines a straight line, well, irrespective of the active coordinate system. So it's basically joining the previously defined key points. And if I look in my geometry, then my first line will join key points 1 and 2. The second line will join key points 2, 3. Line 3 will be joining key points 4, 5, and then it will be 5, 6. And then we have 3 more lines vertically. And this is what we are doing here. So, and here I'm writing a comment also which line number it is, because I mean, later on I will need to know the number of the line if I want to apply specific boundary conditions on the line. That will be very convenient. So while creating these lines, I'm also following the line numbers. I can unfortunately not control the numbers of the lines as I can for the key points. But at least I know that in the order that I create those lines, this is the numbering, what will be assigned automatically by ANSYS. So the first time you issue lstr command, that will create line 1 and so on. I will now copy paste these commands in the command window of ANSYS so that you see that those lines will be created. So you see, well, they're not there yet. If you want to plot something while using this interface, because well, now and then you will need to use the interface, of course, just to review your results as well. You can go to the main menu and say, not the main menu, but this utility menu, go to plot, and then you can select what you want to plot. Lines, for example, will give you the lines. Plot areas will plot you the areas, but of course we don't have any areas, so we just see the lines. And then there is also, under the plot controls, there is numbering, which will bring up the following window, and you can dig here or check these line numbers in this case and say okay. And now you see we have the line numbers. So we see which line has been assigned to which number, and it has this L1, L2, L3, L4, and so on. I'm just using this magnifier, but I think you should be able to see that each line has a different number. And also it's also displayed different colors, but under this plot controls, you can also select that you want to see, I don't know, numbers only. So you see just white lines with the with the numbers. So I will jump back to the default settings. So we have now created the lines, and the next stage is looking at the code we left off here. We created the lines, and now we create the areas. And for that we use this AL command, as you can see, and we use this command twice because we only have 2 areas, and each area consists of 4, is defined by 4 lines. And then I can just jump to the help section and see more in detail about. Go to the A commands and AL. So you can read that the AL command generates an area bounded by previously defined lines, and then you just have the line numbers which are defining this area. So by looking here in this geometry, I know that the first area will be this. If I want to, let's say, create this area, just specify the line numbers 1, 5, 3, and 6. And for the second, it will be 2, 6, 4, and 7. And this is exactly what you can see here. So the line area 1 is created by this set of lines, and the second area is created using this set of lines. And then in the comment I write here the area number, because later on I might need to refer to an area to apply a certain boundary condition or element type, for example. So I will copy paste these commands, and you will see that 2 areas will be created, and you can go to the plot controls numbering, for example, and this time choose the area numbers and then plot the areas actually. So you now see the two different areas with different colors. And this one says A1, and on the right hand side you see A2. The next block of commands that you see is related actually to meshing. We're not doing the meshing yet because to make a mesh you need to specify the material properties and the element type. However, we can smartly control the mesh size by specifying how many divisions we want to have on each line. And this is what we are doing here. We are using these commands. You can see this L cell, which is to select a specific set of lines. And then we use this command LE size, which will pre-assign how many divisions we will have on each line. The more divisions we have, the more refined the mesh will be. The fewer divisions on the line we have, the coarser the mesh will be. So here you see it's just, in principle, just two commands used. The L cell, which for selecting lines, and then the LE size, which is to control the size of the number of divisions that we'll have on these lines. Let's have a look first in the help regarding the line selection. We have now defined 7 lines, and to do some operations, of course, you need to select a certain amount of lines. There may not be just one line, but a set of lines, and for that is very convenient to use this L cell command, which is to select the line, a subset of lines rather. So you can see there that we need to specify here the type, the item, component, the minimum, maximum value, and so on. There's a lot of fields you can use, but we don't need necessarily to use all of them. The type is necessary actually, because here we are selecting, we're making a new selection. So in the type, we should have S enabled, which will select the new set, and that's also a default setting. If you're unselecting, for example, from a set, then you choose the U, for example. If you want to add to the current selection, then you write A. If you want to reselect from the current set, then you say R, and so on. In this case, we'll make a new selection, which will be, and therefore we have as a type, it will be S here to select a new set. And then item, I mean, we can have different options here if we want to use a graphical interface. Since we're not going to use graphical interface, then we leave the item blank, and also the component field will be left blank. And we will then just specify the minimum and the maximum value here. So for instance, if I want to select lines 1 and 2, I will type this command, lcell, and then S, it will be new selection. Then I will leave those two fields blank, and then I'll write 1 as a minimum value and 2 as a maximum. And well, increment will be, for example, 1 between the line numbers, and then this will effectively select lines 1 and 2 from all the defined lines. If I write it from 1 to 3, it will select, and the increment is 1, it will select lines 1, 2, and 3. And if I specify the increment here as 2, then if I write to select lines from 1 to 3 by the increment of 2, it will only select lines 1 and 3. We'll see that now as we move in as we have another look at this input file. So what we are doing now is that we are selecting lines from 1 to 3. We make a new selection, and we select lines from 1 to 3 by the increment of 2. So effectively, we are selecting lines 1 and 3. And why do we select those lines? Because those are the lines with the same length, lines 1 and 3. So, and then we want to specify that on these lines we have the same number of divisions. And then after selecting those two lines, we say that we want to kind of pre-divide these lines with a certain number of divisions. And for that, we use the LE-size command. And well, let's have a look at the LE-size command and what it's doing. So it specifies the divisions and spacing ratio on unmeshed lines. So we start by issuing this command, and then we have some input fields after that we need to specify. And the NL1, for example, is a number of the lines, but we can just write all in this field, which means that we will apply it to the all lines which have been currently selected. And remember, currently we have selected lines 1 and 3. And then we have here options to specify the size, the angular size, number of divisions, spacing, and lots of different parameters. We're not going to use all of them. We'll just specify the number of divisions. And this number of divisions will be, I mean, if we say right here 20, this means that this line will be kind of pre-divided in 20 smaller lines, which will be then used when the mesh will be generated. It will have 20 elements along this length. So if we look in the code, you will see that we have here the LE size. We apply it to all the lines which have been currently selected. So for lines 1 and 3. And the number of divisions that we are writing is equal to RF times F. So this is maybe a bit interesting. So what does it mean? RF times F. Well, these are the parameters which have been defined previously, and RF is the fiber radius. So it's actually the length of this of these lines. The length is RF, and then was multiplied by F. So this F, if you scroll down, you'll see that this is this mesh refinement factor. So it's set to 100. So the number of divisions here will be the fiber radius times 100. So it will divide it into that amount of divisions. And why to include this F parameter there? Well, this is actually the main reason we introduced this mesh refinement parameter at all, is because we want to control the mesh refinement generally in the model. And if we specify a larger one, we'll get more refined mesh, which will have much more divisions on each line. And if we specify a smaller amount of number of divisions, it will be much rougher mesh with smaller amount of divisions. So in this way, by including this parameter parametrically, when we specify the number of divisions, we will not need to do that individually when we want to change the mesh. We will just modify the value of F at the beginning, and it will then affect all the command lines which include it. So you will see how it will work. So it will effectively refine the mesh with the help of one parameter, which is very convenient when you need to do your convergence analysis. Okay, and once it is done for the first set, so we have now, okay, let's copy paste so that you see the effect. Let's paste it in the command window. I'll just copy paste, and you see, probably not, I will try to magnify, but you see this line becomes like a dashed line compared to the lines which have not been affected yet. These two lines belonging to the fiber area have been now dashed, which means that they have been pre-divided into those elements. So it seems rather refined mesh already, but if we don't like it, we can then change the F parameter to a smaller number, and it will be smaller amount of divisions. Okay, so now we will do the same thing for the rest of the lines. We select lines 2 to 4 by increment of 2, and we get then we will specify the number of divisions on those lines equal to Rm minus Rf times F. So where does this come from? Well, Rm minus Rf, if we look in the geometry, is just the length of these lines here, representing the matrix area. And we again multiply the length. We specify the number of divisions as the length of the line times this mesh refinement factor. And in that way, we will divide all the lines at the same ratio, and we should obtain really like square-shaped elements, which should be quite good for the accuracy. Alternative, I mean, this is maybe not so, let's say, perfectly clear. Why do we need to do this selection 2 to 4 by 2? Of course, alternatively, you can select lines 1 by 1. But what I have done, I have squeezed all these operations in a small amount of command lines as possible, so that you can do as much as you can using one line, because you should always strive towards writing as short codes as possible for, say, for your own sake, so that you can easier understand what is being done there, and it's also probably easier to process by the program if you have smaller amount of commands. But alternatively, like I said, you can just select one line, then you can add the new selection, and at the third line, fourth line, it's not really like it's forbidden, or that's the only way, but this is maybe more efficient, that you do kind of smart selection and you select everything you want using one command line. And so we just repeat this procedure for all the lines. I can copy paste the remaining lines of this code in the command window. I mean, normally this is not how you work, that you are pasting commands here. I'm doing that only so that you see the effect on screen. So otherwise it may be quite difficult for you to follow. But normally you just write the code, and then you, even if it's not finished, you can read input from. That's much more efficient than copy pasting here. So now you can see that we have all our lines kind of pre-divided. On the right hand side, you also have some controls which I never talked about, like you can have different preset views, like these 3D views, but we only have a 2D model, so we don't need to have any 3D view. On the bottom right here, we have, if you click this button, this allows you to drag your model around this screen, so that you can, and just by scrolling, you can zoom in or out to observe some details of the model when you need them. And then you have here a fit to screen that will just bring it to the middle. So you can check out these buttons here, what they do, and you can do some different rotations around, but it's not really that necessary. You can just work with the 2D model at this point, and probably you only need to maybe drag the model around to get the zoom in and get more details on it. All right, so far so good. I hope at least everything is perfectly clear to me. I hope it's the same for you. The next thing is to define the element type. And we do that with the ET command that defines the element type. And as always, we can go to the help and see what this command is about. ET, here it is. So the ET command defines a local element type from the element library. We're not going to create our own elements. We're going to use the elements which exist already in the library. So then we take appropriate element from the library. And regarding the element library, you have in the help section, you have also element reference. So if you expand that, you can check out the element library here, and you see it's a lot of elements in the library. And the one that we are going to work with is plane 183. Let's check that out then. 183, here it is. Alternatively, you can search in this window for a specific element type. You see here a description for the element plane 183, so it's a 2D 8-node or 6-node structural solid. We're going to work with mechanical problems, so we obviously need a structural solid element, and you can read everything about this element here in the help. More importantly, it has some parameters that you need to specify when you create the mesh. In this example, if we zoom in here, so with this command, we define the new element type, and we assign it to number 1. And this is plane 183, that's the name of the element from the library. And then you see we have 2 commands there for the key options. And how do I know what to write here? It actually comes from reading the help section about this element, and scrolling down you can see the key options. You can select between the quadrilateral elements or triangular elements. I would recommend these 8-node quadrilateral. Will get better accuracy because triangular elements may artificially increase the stiffness. That's one thing. And the other key option is about the element behavior, and that's extremely important. If you also remember the lecture, that we can have different 2D models but different behaviors depending on how the physical system really is supposed to work. And in this example, we want to make an axisymmetric model with axisymmetric behavior. So therefore, we use here for the key options 3, we specify element behavior with the number 1, which means axisymmetric behavior. So hence, in this command list here, we have key option for the element type 1 set to 0 for the quadrilateral shape elements, and the key option 3 is set to the value of 1, as I explained, because we want to assign axisymmetric behavior. Well, it follows that if you put the wrong number here, you will get, if you put 0 instead of 1 here, that's good enough for you to make a significant error in your calculation. So you should be extremely careful in throughout writing the file. This code, one small mistake means that you'll not be able to get the correct value. So that's how it works with writing a code wherever. It's just enough with one error so that things are not working as they should. Okay, I will copy paste these lines in our command window. You can go to the preprocessor if you want to use this interface, and in the element type and add edit delete, and you can see that we have here the plane 183 element defined, and you can check the options. Then this window will appear and you see that there's quadrilateral behavior shape and the axisymmetric behavior, so that's okay. So there is some ways you can check that your commands have been properly understood by ANSYS. Okay, moving on to the next stage. So the next stage in the file is the input file is the material properties. And now we have 2 different materials, right? We have the fiber, and then later on we have the matrix. So to specify the material properties in ANSYS APDL, we will be using the MP command, which is material properties. And then it has to follow the certain list. As you can see here, since we are going to have transversely isotropic material, we are obliged to specify 9 constants, although it would be enough only with 6. Unfortunately, ANSYS does not have this transversely isotropic option, so if it's some way anisotropic, you need to specify all 9 constants as you would do for any generally anisotropic or orthotropic material. So that means that you have to provide a list of 9 properties for the fiber. And for the matrix, since it is isotropic, the situation is not that bad because you only have 2 constants that you need to specify, which are the modulus in the x direction and the Poisson's ratio. What you see here in these MP commands is that first field specifies the property, that is the EX. For example, that is the modulus in the x direction of the ANSYS coordinate system. So now your job is to translate this from the your job is to translate the local coordinate of material properties that you have into the ANSYS coordinate system. But it's fairly easy to do. Let's have a look. We need to specify the elastic modulus in the x direction for material 1, and we are specifying it to be equal to E2F. So why is that so, for example? Well, it's because we have here, if we have a look, this is the model we are generating, and this is the fiber. And the x direction in ANSYS matches with the direction 2 from this local coordinate system. So then obviously the EX will be equal to E2 from the inputs. And we have the inputs defined already at the beginning of the file. So you have enough kind of supplied material to figure this out, but this is something you need to do carefully in order not to make a mistake here. Especially pay attention to the Poisson's ratios definition, because well, you just need to really translate the coordinate systems correctly. For example, ANSYS is asking for Poisson's ratio xy, and translating it means that you need to specify the Poisson's ratio to 1 of the fiber. And how do you know the Poisson's ratio to 1, like the minor Poisson's ratio? For that, you have these equations that you can transfer them. If you know Poisson's ratio 1, 2, the major Poisson's ratio, and if you know E2 and E1, you can always recalculate. Also, you can also calculate the minor Poisson's ratio and vice versa. Okay, so just be careful when you specify these properties that you are translating these coordinate systems correctly. And for this model, it's one set of coordinate system. And if you are modeling the transverse unit cell, then it's a different one. So you will have to think a little bit there to be careful and to specify the properties of this transversely isotropic material correctly. As for the matrix properties, it's just 2 constants that we need to specify. And really make sure that you specify all the 9 constants for the transversely isotropic fiber, because if you leave some of them blank, then ANSYS will take the value 0 as a property for the corresponding field, which will not be the correct representation of the material. So, and as for matrix, since it's isotropic, it's enough just to specify the 2 properties. You don't need to specify all 9 properties for the matrix. So I'll copy paste this in the command window. And now we can also go to this user interface under the preprocessor, under material properties. You can double click or single click the material properties, and you see that we have 2 materials. One is linear orthotropic, the other is linear isotropic. By double clicking, you will get the window which will show you the properties that you have specified in the code. And for the isotropic fiber matrix, you see there's just 2 numbers. as there should be. Okay, the next stage is then the meshing. We have defined the element type, the material properties. So what we are doing here is now we are selecting the areas because we have two different areas representing two different materials. We first select area number 1 using a very similar command to line selection, but this is for the area selection. So A cell is to select the areas. We make a new selection and we select area number 1, which happens to be the fiber area. And then we use this command AATT, which is the area attributes command, which allows us to specify all kind of, let's say, material properties and the element types to be associated with this area. So if we have a brief look in the ANSYS help regarding in the command reference, we can check under the A commands. We have this, the area attribute command. We can check what are the input fields. So we have there, the first one is to define the material number. So we have fibers as a material number 1, so we'll write 1 for the time being. We don't have any real constants for this one. And then the type is the element type number associated with the selected unmeshed area. And we do that, as you could see there. The material, we select area number 1 and we assign that it will be have the material type 1 and the element type 1. And then we select the second area, which is the matrix area, and we assign that area to have material 2 properties, which are the matrix properties. And 1 is the element type. So what is significant here is that we use the same element type for both areas, but each area has its own material properties because we are representing a composite material consisting of 2 different phases. So that's important to understand that. So I'll copy paste this in the command window, and we have assigned the corresponding areas to the correct materials and element types. And then we have their command to select everything back because we did some selections. Now, before we do the meshing, we have to make sure that we have selected all the model back to its kind of full size, and then we do the meshing. If we fail to select everything back, we can just end up meshing with one part of the model, and then we'll not be able to solve the problem. So therefore, it's important to select everything back and then mesh everything. So we will do that right away. So I copy paste this, and there you go. You can see that we have elements there. If you go to, for example, plot controls, and in the numbering, we can say go to here in the element attribute numbering, select material numbers, for example, and okay, you can see that we can make sure, I mean, at least visually check that we have the fiber area assigned to material 1 and the matrix area assigned to material 2. You can check it just by saying, well, if you really zoom in, you can see this number 1 on each element, and then we see there's a number 2 here on the matrix elements, and they're also in different colors. So this is just a way you can double check that, again, these commands have worked properly. Right, so we have done the mesh, but we need to apply loads and boundary conditions. And that is the next stage. And to do that, we start by applying symmetry boundary conditions, and then we will apply displacement. Just a quick reminder of the boundary conditions. coming back to our model. This is our axisymmetric model, so we'll apply symmetry conditions on the bottom horizontal lines and also on this axis of symmetry. Well, actually, we will not need to specify this axis of symmetry, because if we assign an axisymmetric behavior, it will automatically default to this condition. So we need to apply the symmetry boundary conditions only to the bottom two lines. And then we'll apply displacement on the top horizontal lines. And this is, if we zoom in the code, this is what we are doing. You see here we select the lines 1 and 2 by increment of 1, and we apply the symmetry condition using a special command which is called DL. This is called displacement on lines, but then you can read yourself in the ANSYS help how this command works, and you see there's a label for the symmetry which really ensures that you are applying symmetry. And once we have applied it, we again select back all the lines, or you can select everything back if you want. I will just copy paste this so that you see. Okay, I'll plot the lines, but if I copy paste these conditions of symmetry, then what is visible on the interface is that you have the letter S here appearing where you have applied the symmetry conditions. The next boundary condition is the displacement, and that we apply on lines 3 and 4. And the value of this displacement is also given here as a parameter, because we already calculated it at the beginning. From the inputs we selected, we want to apply 1% strain, and we calculated what displacement we need to apply. So we can just refer to this parameter. And the critical part here is that the direction for this displacement is in the y direction, right? We want to load, or we should be loading this model in the vertical direction, which happens to be the y direction in ANSYS, because we want to calculate the longitudinal modulus, not something else. So I will copy paste the displacement part, and you will see on the interface how it will look like. So we have here like triangles on these lines specifying that there has been a degrees of freedom boundary condition applied on these two lines. And yeah, that's as much as you can see in on this interface. So that actually completes the preprocessor stage. Quite a long stage and lots of things to specify. But now we have done all, like the geometry, material properties, element types. We have done the meshing, applied the boundary conditions, and now it's time to enter the solution stage. So we do that by writing this command here with the / and then SOLU to enter the solution stage. And that is a really short stage at this point. We just write or use one command there. We enter the solution stage and we solve the problem, and that's it. So let me just copy paste it, for example, so that you see. Okay, and then you'll see a window that the solution is done. And that was really quick because the problem is relatively small, and the mesh refinement is let's say manageable by this computer at least. So we have now done the solution, and the only thing remaining is the post-processor stage. So to enter the post-processor, we issue the command with the / and post1. You can again read in the ANSYS help how it works, but I mean, it's just enough to write this command. And then this means we are in a post-processing stage. And it's important really to enter it if we want to manipulate the results, because at the preprocessor, you will not be able to access the results, or at the solution stage, you will also not be able to access the results. So it's the post-processor where you can check the results, and you can do some operations with those results, do some additional calculations. So what we are doing here first is that we are selecting lines 3 and 4 by the increment of 1. So this means we select lines 3 and 4. And then we select the nodes on these and we list the forces. So why do we need to do that? Of course, we need to do that to calculate their reaction force. We applied the displacement. We even know the value of the displacement that we applied, but we don't know the resulting force. And we need this resulting force in order to be able to calculate the average stress, which we need in turn to calculate the elastic modulus. So for that reason, we select the load application surface, which are these lines 3 and 4, according to the numbering that we used in our model. And once we select them, I will bring up the code again. Once we select those lines, we select the nodes associated to those lines, because we can only extract the nodal forces from nodes. So we need to select a certain set of nodes. And this command, this NSLL, selects the nodes which are associated to the selected lines. So it's convenient to select the lines first and then the nodes which belong to these lines, because by selecting individual nodes which also have some arbitrary numbers which you don't know, that will be much more cumbersome to do. Hence here you can see the importance of actually following the numbering of your geometrical entities in the model. Like if you know the numbers of the lines, you're in total control of reviewing results, extracting certain parameters, and without a doubt you can really select exactly what you want, and you can select it fairly easily. So I highly recommend that you, whenever you create a geometry, you always know which line has which number, so that later on you can refer to this line and do the operations. So we select all the nodes which belong to those lines, and then we issue a command which is called the fsum and all. And what this command does, the fsum, if we browse for it, the fsum, here it is. It sums the nodal force and moment contributions of elements, okay? And this is exactly what we want to do. We want to see what is the sum of the nodal forces at these nodes. That will be this reaction force that we need. And once we issue this command, oh, let me do it in a better way. I will copy paste these 3 lines so that you see what actually happens, let's say on screen. Well, you'll, after issuing these commands, you'll have a window showing the results of this fsum command. And then you see different force components and their corresponding values. And you can see that we have a non-zero x component, but it's really to the power of -6, so really negligible compared to the largest component, which is the force in the y direction, which is to the power of 10. So this is also a way to double or to check that you have done everything correctly, because obviously we loaded in the y direction, so this is where we should have the reaction forces, and we didn't apply any load in the x direction, so this is where it should be really small or 0. But this is then the value, this Fy, that's the value of the summation of these nodal forces. That's basically the reaction force. So how do we get this number usable in our code? We need to extract its value, and we do that using the get command. Get command is really capable of really a lot of things. So if you go to the help and read about the get command, you'll see that it's more than 20 pages, I would say, of information, because it can be used in preprocessor and post-processor as well. So it has a lot of capabilities. But if you use this get command, and if you read about it, you can actually define a new parameter based on the internally calculated results in ANSYS. So then using the label fSum and selecting the item, the component in the y direction, because this is the one we are interested, we are able to save or create a new parameter which is called this sum with this slash fl, which is just an arbitrary name that you write, but this will be the parameter which will be assigned the value which will be equal to the result of this fSum command that you just issued. So this is a very convenient way how to save or create parameters after you have done the solution, because then you can basically perform operations and you can calculate elastic modulus right in the code. You don't need to kind of extract number by number and then do some hand calculations. You can just complete the code until the end. So after doing this get command and saving this parameter, we select back everything, and then we using these set commands, or well, that's just one way, but you can use this approach that you can set or you can calculate the new parameters, and then you write just the equation for this. And what is this equation that I'm writing here? It is actually nothing else than the expressions that you see in your slides. So we have average stress. So first I'm calculating the average stress in the code by dividing the obtained reaction force with the cross-section area. And then I will divide this average stress with the applied strain, and I will obtain the elastic modulus. So back to the code, you can see that this is what I'm doing. I'm creating a new parameter called the average SL, stress in longitudinal direction, and that is -1 is because the reaction force is negative to the applied one. So, but it just inverts the sign because the modulus, elastic modulus, has to be a positive value, while the reaction force can be negative, of course. So then it's just this reaction force divided by pi times the radius of the matrix squared. Actually, this double multiplication means that you are raising to the power, maybe a little bit different than in MatLab. Or you can just type Rm 2 times, it will be the same. You just need to have a square of the Rm, okay? And then it's the average stress divided by the applied strain, and you have a parameter EL. Just to finish up with this code, then we select the key point, because what we also need to do is to calculate the Poisson's ratio. We can obtain this information also very easily. We can just select the key point that we know the number of, for example, key point 3. If we refer to the geometry, the key point is here, so it's on the outer surface. And if we know the deformation in the axis 2 direction, then we can estimate the Poisson's ratio, right? So all we need to do is to find the node which corresponds to this key point and check what is the displacement of this node in the x direction, and then we can use this displacement to find the Poisson's ratio. This is exactly what we're doing here. We select the key point first, then we select the node associated to this key point. So for that we have this specific command, and then we again use the get command to define that this will be the x displacement of this node. Well, this is just an arbitrary name, and then you have different components, but you can read about it in the help of this get command. Okay, so we are getting the number of this node, and then we are creating a new parameter. The displacement for this node in the x direction is equal to the, or you can use this kind of, this is the way you can extract the displacement of the nodes using this function. Ux is a function in ANSYS APDL, and if you and here in the brackets you need to specify the node number. So for whatever node you want, you can get the nodal displacement. And the trick here was to find the number of this node so that we can get the correct displacement. And once we have found the displacement in x direction for this node, which belongs to the key point 3, then we can select everything back and calculate the Poisson's ratio according to definition, well, using this set command. The definition is, of course, here. We just discussed it. And now let me copy paste these last operations here. So I have copy pasted everything. So I can go to parameters and the scalar parameters, and I can check the values of those parameters here. And here I can see this is the value of the longitudinal modules, which I just calculated. And it says it's 1.6657 and so on to the power of 11. Since I was working with pascals, this means that it's quite a lot of pascals, but in GPA, it will be to the power of 9, which will mean that this decimal separator moves to places to the right, meaning that I will have the longitudinal modules equal to 166.577, right? Which is good news, I think, and I hope you agree, because in this example that we did with the MatLab, we obtain the same result. So that we have a nice agreement for the longitudinal modulus. Let's check the Poisson's ratio. I have the parameter for the Poisson's ratio. The name for me is NLT, so I'll look up for it. It's here. So you can see it's 0.2693. Okay, that's already, I know that it's in a good agreement with my MATLAB calculation, which was N12 here. So here we had 2693. So I would say it's almost identical result.